We will talk about state machines. Okay. So basically, state machine is like any task we divide into certain states. Okay, and then we do different things in those states, and that is called a state machine. So basically, and that state can occur uh, for a certain duration. So basically, the state remains same for a certain duration, and then it changes to another state, and then keep moving between the states. It's called state machines. Okay. So let's say this one state, this second state, this third state, fourth state, two, three, four. Okay. So it's it rotates between these states. It can go here to here, or come back from here to here. It can go here to here and come again, come back here to here. Where means there can be multiple ways to come back to other state. Okay.
The state is like the previous state we say in the flip flop is similar to that.
What?
In the flip flop or sequential circuits, we say the state, right?
Yeah.
The
So state is like a yes. That is a state is like means any condition like so it changed to the another condition after a certain period of time.
hmm.
So that is called state. Okay. So this duration can be one cycle, minimum one cycle. Okay. Any change, any state will be at least one cycle. Okay. Minimum. It can be more. It can remain in the same state. If it's remaining in the same state, we say we will remain like this. But, okay, we say like this. Okay, in same condition. Okay, same state basically. So any transition occurs to the same state, if it will remain in the same state. Okay, and then we can select that state is that state is more than one cycle. Okay, if it's remain in the same state. So that's why we call it sequential state machine. So sequence is a sequential circuit. Why sequential? Because it occurs for certain time. Okay, that's why it's a sequential. And it executes sequentially states. Okay, sequentially means there's no parallel execution of states. At one time, only one state will execute. Okay. Mhm. Then we have and how we represent a state. So this is called a state diagram. Okay. And state diagram, how we represent it, like each circle represent a state. Okay, and each circle we can name to the name any name. So we can say S0 or S1 or S2, any name you can give. And there could be a there is possibility of transition from current state. So which state we are in, that is called current state. Okay, current state. And by having some transition, we move to next state. So basically, this is next state transition. Next state transition. Transition occur with any condition or always without condition. Without condition means like irrespective of condition, it immediately moves to the next state. Okay, so how we can say transition? So when we transition, like it transition based on some input condition. So input condition we say like in. Okay, so how we represent the transition? So in we say in and then by output. Okay, and uh, and then next state is this. Okay, in by out basically. Similarly, any transition will occur and in by out. Okay, in by out. Okay. So when we represent the state as in by out, so we are representing some output, right? Some output transition or output assignment also we are doing. So this is called Mealy state machine. So there's two types of state machine. One is Mealy and second is Murray. Mealy state machine, how we represent like we always have a in by out. Okay, so we whenever there's a in transition is and there be out also. But at the same we assign output also. While in Murray state machine, in will give you just a transition, okay? But output will not change with the in transition, okay? Output will change only in the state. So here like uh, this is S2, S1, S0. So output will be with the state only, okay? Out. So output is changing only in the state, not with the transition. So this is called Murray. You understand this Mealy and Murray?
Yeah, more state machine. It is it is not considering the output of that first.
The Moore state machine output is only changing in the state,
Hmm.
okay? In the current state, basically. While in Mealy, the output is changing in the transition itself. Whenever input is changing, output is also changing. Okay?
Hmm.
So there's advantage of Mealy is that like you could represent the state machine with lesser number of states, and while while advantage of Moore machine is like the output is always consistent with the state. So that is the difference. But Moore will take extra state to represent the same logic. Might take one extra state, while Mealy will take one lesser state compared to Moore, was for the same logic. Okay,
Okay.
so there's a but here the output will be like consistent in the state, and
Hmm.
here it will be having output into while transitioning also and in the state also. The output is like while transition also happening.
Hmm.
That is difference. Okay. Mm. So let's design a state machine. Okay. Maybe we'll design a simple sequence detector. Okay.
Hmm. Hmm.
So let's say we are getting a stream of data. Okay. Stream of input of basically you can say bits. Okay. Stream of one bit. Okay. And which is changing like this is clock. Let's say, and the stream can be changed like any stream. So this is stream of input. Okay. This n and this is clock. And whenever the stream is let's say 1011, okay, in the sequence of whenever we see the stream uh, last four bits are 1011, we say output 1. Okay, at the same time we detect it basically when the stream was 1011 in the sequence. Okay, so we say say, so we have to detect basically. So it's a sequence detector.
Sequence, like what type of sequence it is detecting?
Any sequence, it is like a fixed sequence. It's always detect a fixed sequence.
Like the repetition pattern or something like
Yeah, this is a pattern. Yeah, so 10. I want to detect a 1011 pattern occurring in a stream of data
that. Okay.
when it's occurs. Okay, understand?
Yeah.
So whenever the sequence it found, it says output one. Okay, basically sequence detected. Okay, so let's say how many state we need to detect the sequence. Okay, so we are designing, let's say, more Mealy machine. Okay, Mealy machine. And to design it, we have to draw the state diagram, right? So Mealy machine is state diagram. SD we can say state diagram. So we start from first state. Okay, first state will always come from a reset state. Okay, init state basically it's called. So whenever you remember I said reset, right?
Yeah.
The reset is like a initialization state. Okay, so whenever we give a reset, it will be at this state always asynchronously first state. Okay, understand?
Yeah.
And so in S0 we want to say like we at least let's say let's say the stream is coming like this 0 0 0. Okay, 1 0 0 0 1 0 1 1 1 0 1 0. Okay, so let's say this stream is there. Okay, so first starting from here. Okay, so it's
Yeah.
saying 0, right? So I say is 0. So when 0 is there, okay, it's remain in the same state. Okay, I said a mealy machine, right? So 0 mealy machine like output is changing, right? Whenever the input is also changed, so output remains 0, right? Because
Mm.
this sequence is not detected. Okay,
Mm.
so and sequence is what our first bit is 1. So right, so whenever we see the first time 1, we'll change the state because we detected 1. Okay, 1 of the sequence. Okay,
Mm.
we detected first bit of the sequence basically. So 0 we remain in there, right? Until 0 is there, we remain in this, right? Because sequence we nothing we detected basically.
Mm.
And then whenever 1 comes, we detected 1, right? Because this our sequence is like 1 is the first bit, right? So we detected 1 bit. So let's say second state is S1. Okay, and then when it will move here, when we see like 1 was there. Okay, but
Mm.
still output is 0 because our full sequence is not detected. Okay, right?
Okay.
And and if let's say next bit is 0. Okay, and what is the possibility that next bit can be 1 or 0, right?
Yeah.
If let's say next bit is 0, so next this is 0, like it's a part of our sequence, right?
Yeah.
It means like one more bit detected of the sequence. Okay,
Mm.
so when we detected one more bit when the input is 0, but still output is 0 because uh, full sequence is not detected. What happens when one comes? So let's say this was 1. Let's say after 1 again 1 comes. What will happen? There's
It will
no
be-
one. We detected
it-
1 bit,
Yeah.
but we again detected 1. Okay, so
Mm.
but it's not. Uh, so it means like it's not a second bit, right? It's still the first bit,
Yeah.
right?
Yeah.
So it means like it's still the first bit. We remain in the same state, right? Because only 1 bit detected,
Mm.
right? A 0 output. And from here, if 0 comes, let's say So if let's say 1 0 bit detected and the next bit is 0, right? So it means like we our sequence is broken because 1 0 0 is not our sequence, right?
Yeah.
So from S2, if our sequence is broken, so nothing is detected basically, right? So we go back to our this state, right? Because nothing is detected there, right?
Mm.
But if one detected from here, so it's our part of sequence, right? So let's say S3. One detected, it's a part of our sequence. So we go here and 1 by 0 basically because one detected, but it's still full sequence not detected, right?
Mm.
1 by 0. And in S3, if let's say one is detected, right?
Mm.
One is detected. So it's our full sequence, right? 1 0 1 0 1 1, right? It's a full sequence.
Mm.
So we say 1 1 because output is also 1 now because its sequence is detected, right? 1
Mm.
0 1. And when 0 comes from here, there's two possibilities, right? From here, S3, if 0 comes, so it means like 1 0 1 and then again 0 comes, right?
Yeah.
What you detected? 1 0, right? 1 0, right?
Mm.
So 1 0 is detected like it should go here, right? Because 1 0 is still sequence is broken, but it's still 2 bits are still detected, right?
Okay.
So this is like 1 0. So this is our Mealy state machine, okay? So
So it will
we-
keep repeating
so
like
here is detected the sequence, and again it keep repeating the same thing. It keep doing the same thing.
step by step it will build that
Yeah,
sequence.
yeah, sequence. Yeah, step by step it will build it. Let's say we want to detect the same thing with the Moore machine. So what would be the like Moore state? So here you see like with the input is changing the state, right? With the input is output is also changing, right? With the Moore machine, what would have been like we would need one more state basically. Why we need one more state? Because from here to here, we when the sequence is detected, we say that state as state 4 sequence detected.
Okay.
So one is there and sequence detected, and in this state we say sequence detected and output is 1. Okay, but you need one extra state. Okay, and then from here you go back to
Mm.
0. Okay, so
Mm.
so what is the disadvantage of Mealy state machine? You see, you need one extra state first of all, right?
Yeah.
And also you cannot overlap the sequence. Why you cannot overlap the sequence? There was possibility like you already you already detected 1 0 1 1 here, right?
Yeah.
There was possibility like you could use this last bit one. Sorry, one more thing. One mistake is there. Yeah. So this is I'll erase first this. So there's two possibility, right? If let's say our sequence is like that 1 0 1 1 0 1 1. So this is also our sequence, right?
Mm.
And this is also our sequence. Okay.
Mm. Yeah.
This bit is overlapped between sequence, right?
Mm.
This bit is overlapped between sequence, right?
Yeah.
Or so this is called overlapping sequence. Overlapping sequence detector.
Mm.
And if let's say we want to detect, we don't want to detect like this. We want to detect like this only. So this is this. If you say we don't want to detect overlapping, we want to detect non-overlapping sequence. Okay. So this is non-overlapping, right? We got 1 0 1 1. Okay. But if you want to detect the overlapping sequence, it means like this transition, basically this transition is already detected 1 1, right? Overlapping sequence. So S3, after S3, it should directly go to S1. Okay. So this is like a overlapping and non overlapping difference. But if let's say I'll go to the next page. Basically, it's better to have a new page. In Moore state machine, let's say we want to detect same sequence. S0, S1, S2, S3. Okay. Yesterday output will be in the state, right? So one detected, right? But still output will be 0 because only one detected, right?
Yeah.
Then with 1 it will remain here, right? It's fine. But with 0 it will come here, right? And still output is 0. Okay. With 1 it will come back. With 1 again it will detect one more one. Okay. And output is 0. Okay.
Yeah.
And one more, since this state is reset state, we cannot say output is 1 here, right?
Yeah.
Whenever new, this is S3, right? And so we need a one more state, S4. And whenever one comes, we say output is 1 here. So this is like you need one extra state to say the output is 1. Okay. But you see a disadvantage here. Like you can never implement the overlapping sequence with this.
Because it is going to the new state.
Yeah. So 1011 011, if you want to implement, you can never implement because this state in the so with this one cannot share the output while detecting the same bit also. So it means like from here, if we can never say this is 1, this because this is also 0, right? So this is a state, not the transition. So in this state, only one output is possible. We see the 0 output already, right? So and also here we have already one is detected, right? If you of if next is 0, let's say. So let's say next is 0. We can directly go here. Okay, let's next is 0. We can go here, and 1 0 is detected. If 0 is there, if 0 comes here from here, okay. Yeah, we can detect overlapping here also. But we need one already. We need one extra state. So let's say here we say output 1, right? Let's say we got this 1 1. Let's say we got 1 from here. Okay, so we come here. Right, 1 we already detected, right? No, sorry. After 1 1, 1 1 1 again. Okay, 3 ones basically. After 1 we got we detected 1, so we come here, and we detected 0. We go here. Overlapping sequence. Okay, so 0, why like this 1 and this 0, 1 0 detected again. Okay, and then again 1 1 comes, it goes here. So it's keep doing 1 1 0 1 1. 1 0 1 1. So here in this state it always detect 1. And
Mm.
if it detect the next one, 1 0 1 1 1 0 1 1 or 1 0 1 1. Okay. It possible, overlapping is possible, but only thing is like one extra state is needed
Mm.
in Moore machine. Okay. So, so you see like I will implement the state machine using the uh, there's two way to implement the state machine. Definitely one is K-map. Okay. So and another is like we directly write the behavioral code. Behavioral VHDL code we can write. Okay. Two ways implementation. Either we derive the equation, write the behavioral code. So we will skip this. Okay. K-map thing, but we'll draw the truth table. Okay.
Okay.
So so to understand how we say the state. Okay. So let's design for this Mealy state machine. Okay. We'll design the truth table for this. Okay.
Okay.
So you see like what is to change the state, what it needs. It should know the current state and the input, right? To
Mm.
change the state, right? So so it was like the so so there'll be a so what we are having in the next state. We are our output is next state and the current state is the input and one more input stream is the input, right?
Mm.
And there's one output. So two inputs are there, current state, okay, and then next state, and then input, and then output. This is CS, okay, and the state is how many bits? Since it's a four state, right?
Yeah.
So we need 2 bits for state, right? So you can say S1, okay, and then CS1, and NS1, NS0, okay. And the N is definitely there, so, okay. So we can write what all possibilities, right? That's how we write the truth table, right?
Yeah.
All possibilities, just right. So now based on the input and the current state, what is the next state? Okay. So this is S0, right? 0, 0. So you can say S0. It can be enumerated, right? Enumeration, you know, right? In C code. So we can
Yeah.
say S0, S0 is 0, S1 is 0, 1, S2 is 1, 0, S3 is 1, 1. Okay. So this is current state S0, right? Current state 0. So when the current state is S0, what is the next state? When the input is 0, it's the
Yeah.
same state, right? So next state is 0. and output is also 0, right?
Hmm.
When the current state is 0, 1, basically this is 0, 1, and the input is 0. So what is the next state? S2. S2 is 2, and output is 0. When the current state is 2, basically S2, and then input is 0, the output is S0, 0, 0. When the current is S3, input is 0, input is 0. Where it is? Oh, so it should be 0. So S2. In the current it says 0, 0, output is 1, it goes to S1, right? S1 is there and the input is 1, it remains the same state. And when the S2 input is 1, it is S3. In the S3 the input is 1, is S1. And but output is 1. Okay. So basically, and I will not solve the equation, but you can solve it. And then your task may be like you can create this. Okay.
The output equation.
The output equation later, maybe not now. But
Hmm.
I will write the VHDL code, behavioral code. Okay. So,
Hmm.
let's start the Vivado.
So I have one question on this table.
Yeah.
The current state and there is a next state, right? And we have the input.
Mm-hmm.
So current state, we are saying the S1 is 0.
Current state S1. S1. Row.
Okay, the first row is input is 0. That
Put
time,
is
yeah, input is 0.
current state is 0.
Current state is also 0. And output is, next state is 0. And
0
output,
because this transition.
yeah. And the next row, we have input 0
Current,
and
current state is 1. So basically, this current state is 1 and put is 0. This transition from here to here.
okay, so this
Because the truth table is not in sequence, right? So truth table is just all possibilities.
hmm,
You understand? Truth table is not your sequence. It not does not follow your sequence. It is all possibilities, and you should decide with all possibilities what is your with the current line, current like basically row. What is the next possibility, next output possible, or next state possible? The table doesn't depict your the sequence of state machine. Understand? So
hmm,
table is like all possibilities.
okay.
Understand? So don't see like why it's not in the sequence.
Hmm,
Uh, that is to table like any way you can write. You can move CS0 to the right side, left side, make it MSB, and then in make it zero, LSB, and still result will always be same.
hmm,
Whatever way you write it,
hmm.
okay, result will always remain same. Like equation of the next state, and then uh, out remains same, irrespective of how you write the. You can move the in to the LSB and CS to the MSB. It doesn't matter. It will always equation will always come the same.
Okay, in VHDL, we generally write the logic in terms of equation, right? Some
No,
equation like out something, then you put some.
That's what equation. If you try to write the equation, right, basically, you cannot write everything with the equation. That's how we do the behavioral code. We write the behavior. Now I will show you the behavior to write the state machine. Okay.
Okay.
So I will give you a task, like you create the equation and you write the state machine code using the not behavior, using the equation.
Equation. Okay.
And I will create with the behavior. Because I don't want to solve the K map. You can solve. You learned already, right? K map, so you solve it.
Okay. So, but how do we know that behavior we are writing that is like correct or not when the logic we are writing?
I will tell you why it's correct. Why it's correct. Behavioral is always correct. We will see. That's how we go and verify the right state machine already created. Some small devices, some problem was there. Create parameter. I can rename sequence it. Let's try the port. So what we have port?
Can you make this window bigger outside? It will, the editor.
This
Yeah, I think it's good.
outside windows. No, that's fine.
Yeah, it is good now.
So we have right one input only, right? One output. So basically, it's a sequence, right? Sequential circuit. So we need a clock, right? First of all, clock. And reset is mind active. Right? These two things are needed. You can say active high. Should always know like what type of reset we are designing. And, then we have input, right? So in we cannot do that. We can take in.
Yeah.
Only one output, right? There is no other output. So now, so you see, like our design was having state names, right? Enumeration, right? S0, S1, S2, and all, right?
Yeah.
So let's so we can enumerate here type in the VHDL type is there to enumerate. Okay, type state is okay. What states are there? S0, S1, S2, S3. Is type. We have to define a type. Okay, so it is like there's a state name is there, which is like S0, S3, S4, S4. Okay, and what it does, we can initialize those states also like this. not initialize. Okay, I'll tell you this. So basically, but automatically tool enable auto tool code it binary. Okay, binary value. What it means like tool will automatically assign a value to S0 as 00, S1 to whatever 01 and S2 to sequence in the sequence. Does not matter how you write this value. Uh, this basically this enumerated value will be the 0 was 0 and this was 0, and in sequence it will assign always.
Okay.
Okay, and we can assign. I'll just go it quickly. Forget how to initialize it. Records. Enumeration type. Over here. So this is how I find out that it is not providing it. Okay, but I guess it's same way it's does it like 0. It's also nobody is initializing it. That's how I also forget how to initialize it. I will let you know next class. But this is also fine. Okay, this will
Okay.
automatically initialize the value whatever we said, right? So now this is a type. We declare a type, right? So but we have a signal, right? Current state and next state, right?
Mm.
So we define a signal CS, right? We have internal signal, right? Current state. We should know. And what is the type of current state? It's a type state. Okay. This type, right? Four CS is like four types: S0, S1, S2. And similarly, next state also is also type. What is the type of next state? State, right?
Okay. Yeah. S0.
Yeah.
So CS we say S0 S1, right?
Yeah.
Next to S2 S3.
In state machine, we always write two process. One is like a process, uh, which is like a clock break process. Clock reset begin process. Okay. We go to the state machine, state diagram basically. The next state is basically current state is so this is the current state, right? Okay.
Mm.
This current state is always So when we move to this state, we from here we are saying we are moving to the next state, right?
Yeah.
As soon as we move there, it becomes the current state, right?
Yeah.
In the next cycle, current cycle we are moving, we are transitioning. But in
Mm.
the next cycle, the same is same. The next state becomes the correct current state, right? Always the next state becomes the current state, always, irrespective of the condition, right?
Yeah.
We are transitioning for next state. As soon as we reach in that cycle, the next state becomes the current state, right?
Yes. Yeah.
Irrespective of any condition. Okay.
Yeah.
So it means like current state is always as a next state becomes always current state in the current time.
Yeah.
Okay. So it means like the previous, basically the uh, like so basically the common previous transition becomes the current state always.
Mm.
So we write the pros and current state. So previous transition becomes the current state. So it was like a memory is that previous, it's a memory, right? The previous one becomes the current state. It's the same and same value. So it means like we assign the previous to the current, and current become the memory. We always remember the current thing, right?
Yeah.
Yeah,
Yeah.
right. We
Yeah.
always remember the current thing, and because previous become and the current thing become previous. Previous thing become current, right?
Yeah.
And previous was our next state, right?
Yeah.
Next state transition. So it means like it means we write a m- memory element. Memory element is basically is a register. What is a register? We always the CS is always the memory.
Mm.
This current state always we know or we remember. Set. Then so when the reset is there, what is the current state? Current it is always
0.
the S0. Okay.
Mm.
Current state will be next state, right? Next state was a transition state. And the transition state always become the current state in when we reach there, right?
Mm.
We remember the next state, transitioning state, as a current state.
So that should be next state equal to current state, right? If it is.
Next state depends on the condition. Next state is not always the current state. Right? Next state
Mm.
is a combination of current state and the input. But
Mm.
current state is always the next state. Like that. From here we are saying we are moving to the current next state, right? Which is next state is S1. As soon as we move there, it becomes the current state.
Mm.
Okay, so
Okay.
it means like the next state is remembered as a current state in the next cycle.
Mm. Okay.
So we are moving to the next cycle, right? And making it a current state.
Current state. Okay.
But now how we design the next state? The next state will be simple, like if else or case anything. I mean, we design a basically we write a behavioral code. So next state I said, right?
Mm.
Next state basically I can comment it. Next state can be a equation or a behavioral code. You write a equation, I will write a behavioral code. Okay. Your task. Maybe I can comment it. behavior. So behavior, what mean by behavior? It means like based on certain condition, I will derive the next state. Okay, and what is a certain condition? It is a condition using the basically leave the truth table. It's like based on the input and the current state, I'll derive it. Okay, so always we there's a certain like way is there where to write is there writing the behavioral code or for the statement is like so again this is also a sequential circuit, right? We are like based on if else or case we'll write it because it's based on a condition, so we always write a case or if we write in the process, so that's how we are using the process. Okay,
Yeah.
and so we write a case of what current state. Okay, is so for current state case, we are writing the end. We're deriving the next state. Okay. Case is four possible values there, right? When S0. Okay. S1, 2, 3. We write. We can write others as S3. We can write both way, right? I said it. If your case is complete, it will not take the others. So you can write either this as others, or you can write this as a S3 and write others null. Okay. But others is always must be written. In S0, what we are doing? In S0, we are depending on input, right? Two possibilities are there in S0, right? Either input 0 or input 1, right? So we write if input equal to 0, input equal to 0, and current state is, sorry, next, we are deriving next state is same, right? S0, right?
Yeah.
Plus it is S1, right? So we write other way. We try to write S1. So here it's like S1 and this remains S0. Condition we write first. It's right. S1, when 1 was there, it goes to S1. If 0 is there, it remains same state. Okay. Now we write, so we can copy paste it, and same thing we are going to write in each state, similar things. And when in S1, the S1 when it's a 1 value, it's remain in the same state. When 0, it's S2, right?
Yeah.
So it's remain the same state, otherwise S2. At the same time, we write output also, right? Because output also we're deriving out P. Two things we are doing in next state and output, right?
Yes.
Output is always 0. So if always 0 is there, right, you can write directly outside. Okay, no need to write like here because both it is going to repeat a statement. So it will ignore the if because both are having same out. We can directly write output here. And in S2, in S2, when the input is 1, it's S3, otherwise it's S0. So input is 1, it's S3. Okay. And in S3 state, if input is 1, it goes to S1 with output 1. And if 0, it goes to S2. So here it goes to S1 with output 1 here. Output. And here it goes to S2 without 0. Okay.
So how do we, I mean, most of the time we cannot derive the equation with the K-map, right?
So that's how we write, right? We don't write the K-map.
So we just try to understand and
Kind of sad. First state machine draw the diagram, state diagram,
Hmm.
and then you create like this kind of code. And then now here the sensitivity list also, right? Input. So sensitivity list input and the current is set. Because on these two it's depending. Let's write quickly the test bench, okay? Science 2, not of club, you remember it? That's 5 nanosecond video. We're writing the nanosecond period, okay? And then process begin and process. Start writing the put right. So and reset we make yeah, reset two way you can write reset. One time we if want to change just reset one side, so we can say reset gets take 0 after 100 ns, okay? Anytime. So basically after 100 ns the reset will become this 0. We say input size 2 take 0 800 ns. Wait, maybe not 100, maybe 120 we can. Okay. Then now we started writing sequence, okay? So let's write Just copy it for us. So we can write wait and after. After we can write like this, okay? And wait for only time will be there. And after we do assignment and after what time we do assignment, it will do that way. The after and
Wait is for holding that value.
yeah, and after will like it is scheduled to assign after that much time. It's already executed the statement, but after but will assign only after that much time. So 0 0. Let's do 1 here. 1 0 1 1. Then again 1 already to 1 0 1 1. Okay. Then we keep this okay. And port map also we have to do. We did not do port map. We'll do named map. Currently not named map, positional map. Because we know, right? We are having the same name.
Okay.
We can try this. Okay. The positional map. Let's run the simulation. You're giving this kind of right. So we given 1 0 1 1. Okay. At this block it is detected 0. We can add if you want we can add more signals. So we can add from the duty also, right? Duty signals are not visible right yet. So we can add object of duty also, okay, to see what how or do. So we can see object of duty is also current state and next state is also there. We can add to the wave, okay. And then once we add to the wave, we have to do this button press. Now we see. You see, right? Initially, when the reset was there, it is in S. Next current state is S0, okay. And when until 0 was there, it will remain in the 0 right state until so it sees like 1 here, okay, and 1 here, and it goes to x1, and s1 will assign to the next state here as a clock edge, right? And each time clock edge is there, the s2 s1 value will assign to the clock edge, right? See, it's to change here, but it's assigned to the clock edge, and so on, right? And see, so this one was detected here at this cycle, and then 0 was detected here, and then again 1 was detected here, and it sees in this state it sees 1, right? So 1 0 1 1 at the same time output is 1, right? Whenever the last one is detected, same time output comes, right? Last one is detected here, and at same time output comes, right? So see, we given a two time same sequence, right? Overlapping sequence 1011 1011. So detected two times.
Hmm.
Okay, and let's see how it's our elaborated it looks like
Hmm.
the semantic. Current state and next state output, and output depends on the state. Okay, and this state derives from the current state and next state. So on. Okay.
So this is the we derived this for 1011 sequence.
Yeah.
Hmm. Okay. So if there is any other sequence, then based on the
Yeah, based on yeah, it will be different. Yeah. So
okay.
basically, your this will remain same. Everything this will change in next state derivation.
Okay. So in this way, I do not. I mean, we don't need to know what is the hardware even needed for that. We are just based on the logic.
Yeah. So that's how we are going to code, right? Like in later stages, like uh, uh, so one more thing, you always don't write like state machine. A state machine is to control certain sequence. In bigger designs, the state machine or states will be like a bigger state. Like in a single state, you might be doing maybe you might be staying for 1,000 cycles, and in those 1,000 cycles, you'll be doing some task. So and basically, you can say like in this state, I am doing a multiplication task. Okay, and then from here you trigger the multiplication, and once the multiplication task is completed, you move to the next state by taking that from that basically that task. So understand. So it will not be a simple stream of input. It may be a trigger from another task, and you could wait in the state.
Okay. So I have one question. We we create these equations, right? Let's say
Mm-hmm.
some
Mm-hmm.
maybe mux, for example, mux
Mm-hmm.
using a decoder, like let's say
Yeah,
16. For example, 16 is to 1 mux is there, and we are using decoder, and there will be some equation also, right? Like in the uh,
yeah,
we'll write some logic, right? Like for that output, for the what with that equation. So
yeah, yeah.
without that equation also we can do like you did, right? Just with
Yeah,
the
yeah, Mux. Yeah, yeah. Mux. I already shown you, right? Mux based on the case and all, right? Written, right? Remember the two classes we did. Mux with the equation and Mux with the cases, right? If else case.
yeah, that was 2:1 was with the equation. There was a 8:1
Yeah,
mux
yeah, yeah,
decoder.
yeah. So I mean to say like you can either do by the VHDL directly, or you could do by the equation. The equation is to just understand like what it implements internally, and otherwise it's you can directly write the case, if else, whatever way.
Okay. Yeah, that is interesting. I will look into it. I have not done. I just did the 2:1 mux. I will look
Okay,
at the that with decoder one 8:1.
okay. Mhm.
All right. Then see you then.
Well,
Um,
I will send you this code, and then you can complete with the equation.
okay.
Or I'll send next class, maybe an hour's night.
Yeah, that's fine.
Yeah.
Yeah, thank you. See you.